Hi there, I'm Lin Long, and today I'm going to introduce our CVPR 2024 paper, Positive-Unlabeled Learning by Latent Group-Aware Meta-Disambiguation. In this work, we introduce Latent, a novel framework for positive-unlabeled learning. Latent incorporates a hierarchical contrastive learning module to address the challenge of ineffective representation learning observed in prior studies. On top of this, in the game we also use meta-learning to enhance the robustness of training by directly distilling the true labels of unlabeled data. Our extensive experiments on benchmark datasets, including CIFAR-10, CIFAR-100, STL-10, and Alzheimer, demonstrate that the game surpasses current state-of-the-art methods, achieving an average accuracy improvement of 6.8%. We also provide comprehensive ablations and visual analysis to validate the game's effectiveness. Next, I will delve into the motivations and detailed designs of our approach. For those who might be unfamiliar with PU learning, let me first provide a brief introduction to its basic definitions. PU learning, short for Positive Unlabeled Learning, is a specialized binary classification task where only a limited number of positive samples are explicitly labeled, while all other instances in the training set remain unlabeled. The primary challenge in PU learning arises from the absence of explicit negative samples, the label ambiguity inherent in the unlabeled data. To tackle this issue, a common strategy in PU learning is to treat all unlabeled data as corrupted negative samples, and reframe the original PU problem as a cost-sensitive classification task through importance reweighting. Another mainstream approach involves selecting reliable negative or positive samples from the unlabeled set to create a pseudo-binary label set, which can then be used with traditional semi-supervised learning methods. Despite the promising results, the two types of PU algorithms mentioned above have significant limitations. For cost-sensitive methods, downweighting false negatives results in a substantial reduction in the effective utilization rate of the training data. For sample selection-based methods, the selection process is not always accurate, which can lead to confirmation bias or accumulated errors. From the analysis above, we can see that, while most previous studies focus on straightforward label disambiguation, there is always a dilemma where model generalizability and supervision intensity cannot be simultaneously ensured. This limitation has caused PU learning nowadays to lag behind fully supervised counterparts. Meanwhile, we observe that in real-world PU scenarios, the binary classes are typically aggregated from finer-grained subcategories. For instance, as shown in the figure on the right, the diagnosis of Alzheimer's disease can be viewed as an inductive process, where the underlying pathogenesis offers a more concrete representation of a patient. Based on this intuition, existing studies may have overlooked the semantic insufficiency of PU data. We argue that the primary bottleneck lies in the difficulty of developing discriminative representations under the constraints of unreliable binary labels. In other words, the ambiguous and semantically poor binary labels are not able to provide sufficient supervision. Therefore, we propose a novel PU learning framework called Latent Group-Aware Meta-Disambiguation, the GAME, to produce compact representations that encapsulate the intrinsic group semantics of PU data. To achieve this, we first design a hierarchical contrastive learning module, which actively explores the latent groups reflecting the essential semantics of PU data. Although contrastive learning has been extensively studied for representation learning with limited annotations, the PU setting presents unique challenges for adapting this technique, primarily in two aspects. The first challenge is, without explicit labels, how can we construct a positive set for contrastive learning that can guide model to distinguish samples from different latent groups? To address this, we leverage unsupervised clustering to artificially define a series of potential subcategories, which can then be used to construct the positive set. By doing so, We facilitate the spontaneous organization of data by manipulating features, leading to better separability between semantically distinct data in the embedding space. However, here comes the second challenge. How can we ensure that the subcategories obtained through unsupervised clustering are useful for enhancing the top-layer binary prediction, as such clustering seems pretty unreliable without any kind of supervision? To better align the latent categories with the given binary labels, we cut off misclustered pairs based on the dichotomized outputs of the classifier, restricting the latent categories to be semantically binarizable. This means two samples from the same cluster are considered a positive pair only if they have the same predicted label. Furthermore, we adopt data-driven neighbor augmentation based on KNN algorithm, which helps distribute the representations more smoothly within local neighborhoods. Thus, the final positive set consists of instances that are either near neighbors or belong to the same cluster centers and yield the same prediction results. When it comes to the label disambiguation module, which enhances the robustness of model training, the game takes a different approach compared to previous methods that rely on importance reweighting or heuristic sample selection. With the enhanced representations obtained through our proposed hierarchical contrastive learning, which provide more semantic info, the model can now better comprehend the relationships between PU data and their binary labels. In the game, we adopt a more aggressive label disambiguation strategy by leveraging meta-learning for direct label refinement. Specifically, we first assign a pseudo-label to each unlabeled instance, which is initialized to 0. We then optimize these pseudo-labels using meta-learning to distill the true labels of the unlabeled data. As the meta-objective shows, in the inner loop, we first acquire model parameters theta y tilde that minimize the classification loss over training data pseudo-labeled with y tilde. These parameters are then evaluated on the support set D sub, which consists of a very small amount of labeled data, which is a common practice in meta-learning. And then, in the outer loop, we minimize the evaluation loss with respect to the pseudo-labels y tilde. Intuitively, the closer y tilde aligns with the ground truth, the less label ambiguity there is, and thus the model trained with it is expected to exhibit better generalizability on the golden support set. In this way, label disambiguation can be transformed into an optimization problem of minimizing the evaluation loss. The corresponding classifier trained with y tilde star will be our target model. However, we can see that such two nested loops of optimization can be very expensive and inefficient. Therefore, we design an online disambiguation algorithm that iteratively adapts an online y tilde and alternates minimization between the inner and outer loop. Additionally, we also exploit gradient projection and exponential moving average to enhance the robustness of label updates. Due to time constraints, I will not elaborate on the relevant details. In brief, by alternatively update y tilde and theta, we iteratively approach the optimal solution together with the distillation of y tilde. Experimental results show that the game significantly outperforms the current state-of-the-art methods by an average of 6.8% of accuracy on 4 prevalent benchmark datasets. We have also provided visual results to demonstrate that the game can indeed learn effective representations that are well aligned with the real semantics. For more experimental details, please refer to the paper.